Hey, time travelers. This is this is a fun problem. I just kind of needed it to wind down for today, and it's just something I think about a lot while I drive. So for those of you who don't know, or for those of you who didn't grow up like in Minnesota or somewhere where it gets really icy a lot of our roads are actually curved. We don't really notice it because it's usually like 5-10 degrees at most. But it's curved in such a way that if someone hits a patch of ice, the friction force comes in, and what was originally stopping them from sliding down the curve allows them to slide down the curve and go into centripetal acceleration. And we'll get more into that, but that's just a fun fact for like Minnesota roads and a lot of parts of Canada, which I also have citizenship for. Fun fact. So we are given, if the turn radius for an exit ramp is 20 meters and the angle of the curve is 5 degrees, what should the speed limit be if the road were to freeze over? So let's just start with our equations. I'm not going to write what we know because it's just kind of all laid out. We have our diagram. So actually, before we start with our equations, let's start with an FBD. FBD. All right, so this is going to be an FBD of our car. Remember, always have your label and a curved arrow to your car, or curved arrow to whatever you're describing. So you're describing our car. And I'm going to put my car like this. This is going to be 5 degrees, and we're going to say this is our axis, with this in the x direction and this in the y direction. So our forces are no longer friction. Friction was what was stopping us from sliding down the hill. Our forces are gravity. So that's going to be our weight force, and the normal force, which is pushing us up. Sorry, I'm like at an angle to my paper. Okay, so we can take our unresolved component of our vector, and we're going to say that the total net force is going to be the weight force in the cosine. Okay. And we know it's this because if it's flat against the floor, this angle would be 0 if this angle is 0. So these are the same cosine, or see, these are the same thetas. So we know that. Now I'm just going to leave that there. We also know that this is equal to mass times acceleration. And this is always going to be true. Your total force is equal to your mass times acceleration. And so this is y points cancel. And we're just going to say they cancel. It's a pretty fair assumption, and it also makes the rest of our math work a lot easier to say we're not going up and down on the ramp, we're just going through it. And so we're going to say that our centripetal acceleration is equal to velocity over radius. And so we want to find the speed limit, and so we're going to rearrange for velocity. So we're going to say velocity is equal to, and so we're going to say that force over mass is equal to acceleration. So we're going to say all force is normal to car. Normal is fine in most math settings, but in normal, I would be really explicit about perpendicular, because you're saying is car's velocity, and therefore is centripetal. So we say acceleration is equal to force over mass. Okay, cool. Let's just plug that in. We're going to have the velocity equal to 1 for mass. We're going to say weight equal to mg. So mass cancel. Ready? Cosine theta times r. And so now we can just plug. We can say 9 and 20 and 50. So we can say that the final, or the velocity required to go around this circle in no friction conditions is 13.97 meters per second. Or for all of my fellow freedom uniters, that is 31.25 miles per hour. And that would be our required speed limit in order to stay on the track at 20 meters. Okay, I hope you enjoyed this. It was kind of a chill video. Good luck, time traveler. You got this.